Russia commands one of the largest and most technologically advanced air forces in the world, boasting over 4,000 aircraft in active service. Its strategic bombers alone can reach targets thousands of kilometers away, projecting power on a global scale. But here's a striking fact. Russia's Tu-160 White Swan remains the fastest bomber ever built, capable of speeds over Mach 2. Do you know what makes this aircraft a game-changer in modern air warfare? Modernization of the Russian Air Force. Modernization of the Russian Air Force. Russian air power in 2025 is undergoing a transformation that's reshaping the balance of aerial strength on the global stage. At the heart of this evolution is the ambitious modernization of the Russian Air Force, driven by the introduction of cutting-edge aircraft designed to rival the best in the world. The Su-57, Russia's fifth-generation stealth fighter, stands out as a symbol of this leap forward. Combining stealth technology, supersonic speed, and advanced avionics, the Su-57 is engineered not just to survive in contested airspace, but to dominate it. This fighter is equipped with sophisticated sensors and weaponry that enable it to engage multiple targets simultaneously, making it a formidable opponent in any aerial engagement. Beyond the Su-57, Russia is upgrading its fleet of Su-35 and Su-30 fighters, ensuring that even its fourth-generation aircraft remain highly capable and relevant. This modernization effort isn't just about hardware. It also reflects a strategic shift toward greater operational flexibility and networked warfare. The Russian Air Force is integrating its aircraft with advanced command and control systems, allowing pilots to share real-time information and coordinate complex missions with precision. This interconnected approach enhances situational awareness and multiplies combat effectiveness. While challenges like budget constraints and aging infrastructure persist, Russia's commitment to revitalizing its air power signals its determination to maintain a credible and modern aerial force. The modernization of the Russian Air Force is not just about keeping pace with rivals, it's about asserting Russia's role as a dominant air power well into the future. Strategic bomber capabilities. Strategic bomber capabilities. How does a nation project power across continents without launching a single missile? The answer often lies with its strategic bomber fleet, and in 2025, Russia's capabilities in this domain remain a critical aspect of its air power. The formidable Tu-160, often dubbed the White Swan, continues to be the crown jewel of Russia's long-range aviation. This supersonic variable sweep wing bomber isn't just fast. It's designed to penetrate sophisticated air defenses and deliver both conventional and nuclear payloads over vast distances. Its recent upgrades include new engines and modern avionics, significantly extending its operational life and enhancing its combat effectiveness. Complementing the Tu-160 is the enduring Tu-95 Bear, a turboprop-powered strategic bomber that, despite its age, remains a reliable workhorse. The Tu-95 has also undergone modernization, incorporating new cruise missiles that allow it to strike targets from standoff ranges, minimizing exposure to enemy air defenses. These bombers are not merely delivery platforms, they are symbols of Russia's global reach and deterrence capabilities. Their presence in long-duration patrols over international waters serves as a clear demonstration of force, projecting influence far beyond Russia's borders. The strategic bomber fleet also plays a crucial role in supporting naval operations and conventional strike missions, offering a versatile platform for various military objectives. The continuous development and deployment of these bombers underscore Russia's commitment to maintaining a robust long-range aviation component, ensuring its ability to respond to threats and project power on a global scale for years to come. Drone and UAV integration. Drone and UAV integration, unmanned aerial vehicles have become a game-changer in modern warfare, and Russia is no exception in harnessing their potential to boost air power in 2025. The Russian military has accelerated the integration of drones and UAVs into its air force, recognizing their value not only for reconnaissance, but also for electronic warfare and precision strikes. These drones provide commanders with real-time intelligence, allowing for faster decision-making and more effective targeting without putting pilots at risk. Russia's UAV programs include a variety of platforms, from smaller tactical drones used for battlefield surveillance to larger armed drones capable of carrying out strike missions. What sets Russian drone development apart is the emphasis on electronic warfare capabilities embedded within these systems, enabling them to jam enemy communications and radar, disrupting adversary operations before a single missile is launched. This blend of reconnaissance, strike, and electronic attack roles makes drones a versatile force multiplier in Russia's aerial arsenal. Additionally, the use of drones in recent conflicts has provided valuable combat experience, helping refine tactics and improve drone technology. The growing drone fleet also complements manned aircraft by performing high-risk or prolonged missions, preserving pilot safety while maintaining battlefield pressure. As Russia continues to invest in drone innovation, including AI-assisted targeting and swarm technologies, its air power is evolving into a more flexible, networked force capable of dominating contested airspace. This shift not only enhances Russia's tactical options, but also signals a broader trend in warfare, where unmanned systems increasingly define air superiority. Air defense system synergy. When it comes to defending vast airspace, Russia doesn't rely on fighter jets alone. Its air defense systems form an impenetrable shield that complements its Air Force operations. The S-400 Triumph system is arguably the crown jewel of this layered defense network, capable of tracking and engaging multiple aerial targets, including stealth aircraft and ballistic missiles, at ranges exceeding 400 kilometers. But Russia isn't stopping there. The introduction of the S-500 Prometei promises to revolutionize air defense with even greater range, faster tracking, and the ability to intercept hypersonic threats. These systems don't operate in isolation. They are tightly integrated with Russian aircraft and command centers, creating a seamless web of detection and interception. This synergy allows pilots to maneuver with confidence, knowing that ground-based defenses cover their flanks. The combination of advanced radar, missile technology, and electronic warfare creates a multi-layered fortress that complicates any adversary's attack plans. Moreover, the mobility of these systems means they can be rapidly deployed to hotspots, adapting to shifting threats in real time. This integration of air defense and Air Force assets exemplifies Russia's approach to modern warfare, combining offense and defense into a cohesive, highly responsive force. As air threats evolve with new stealth and hypersonic technologies, Russia's layered air defense network ensures it remains a formidable challenge for any potential aggressor aiming to penetrate its skies. This strategic blend of technology and coordination is a key pillar of Russian air power in 2025, making its airspace one of the most heavily defended in the world. Electronic warfare and cyber capabilities. In modern aerial warfare, dominating the electromagnetic spectrum can be just as decisive as controlling the skies. Russia's investment in electronic warfare and cyber capabilities has become a cornerstone of its air power strategy in 2025. These advanced systems are designed to disrupt enemy radar, communications, and navigation, effectively blinding and confusing opposing forces before a single missile is fired. Russian EW units can jam or spoof enemy sensors, degrade targeting accuracy, and protect their own aircraft from detection, creating a significant tactical advantage. This electronic dominance extends beyond traditional jamming. It includes cyber operations that target command and control networks, undermining enemy coordination and response times. The integration of EW capabilities with manned and unmanned platforms allows Russia to conduct complex operations where electronic attacks soften defenses and pave the way for precision strikes. Recent conflicts have demonstrated how Russian electronic warfare can neutralize technologically superior adversaries by exploiting vulnerabilities in their systems. This layered approach to electronic and cyber warfare not only enhances survivability, but also forces opponents to adapt costly countermeasures, slowing their operational tempo. As air combat increasingly relies on sensors and data, Russia's focus on EW ensures it remains a formidable force capable of shaping the battlefield environment itself. This blend of electronic disruption and cyber offense is transforming Russian air power into a multi-dimensional threat, where control over information and technology is as critical as firepower. Training and readiness. What separates a good pilot from a great one? In 2025, Russia's air power relies heavily on the skill and readiness of its aviators, who undergo rigorous training designed to prepare them for the complexities of modern aerial combat. Russian pilots don't just fly, they train in highly realistic simulations that replicate the intense pressures of real battle, including electronic warfare environments and multi-threat scenarios. This continuous, immersive training sharpens their reflexes and decision-making, enabling them to operate advanced aircraft like the Su-57 and Su-35 with precision and confidence. Beyond individual skills, Russia emphasizes teamwork and coordination, conducting large-scale exercises that integrate air, ground, and naval forces to simulate joint operations. These drills test pilots' ability to adapt quickly, communicate effectively, and execute complex missions under stress. The Russian Air Force also invests in updating its training infrastructure, incorporating virtual reality and AI-driven tools to enhance learning outcomes. This focus on readiness ensures that when conflict arises, Russian pilots can maximize the capabilities of their aircraft and systems. Despite technological advances, human expertise remains a decisive factor in air superiority, and Russia's commitment to pilot training reflects an understanding that cutting-edge hardware is only as effective as the people who operate it. In a rapidly evolving battlefield, this blend of advanced technology and elite training keeps Russia's Air Force agile, lethal, and ready to face a wide range of challenges. Export and international influence. So, how does a country extend its influence beyond its borders without firing a single shot? Well, Russia's air power strategy in 2025 really leverages military exports as a powerful tool to build alliances and project influence worldwide. By supplying advanced aircraft like the Su-35 and MiG-29 to allied nations, Russia not only strengthens these countries' defense capabilities, but also deepens strategic partnerships. These exports come with training, maintenance, and technology transfers that create long-term dependencies, ensuring Russia's presence in key regions. This approach goes way beyond just selling hardware. It's really about shaping geopolitical dynamics through military cooperation. Countries in Asia, the Middle East, and Africa have become major recipients of Russian aircraft, benefiting from proven technology at competitive prices. This export strategy also fuels Russia's defense industry, providing funds that support further research and development. Moreover, by showcasing its aircraft in international air shows and joint exercises, Russia demonstrates the reliability and effectiveness of its air power, attracting new customers and, reinforcing its global standing. This blend of commerce and diplomacy through military aviation helps Russia maintain a foothold in regions critical to its interests, even where direct military presence is limited. In 2025, Russian air power isn't just about what happens in the skies over its own territory. It's also about extending reach and influence through the wings of its allies, making military exports a key pillar of its broader strategic vision. Challenges and limitations. Even the most advanced Air Force faces hurdles, and Russia's air power in 2025 is no exception. Despite some pretty impressive modernization efforts, there are several challenges that threaten to slow progress and limit operational effectiveness. One of the biggest obstacles is budget constraints, which really impact the pace of aircraft production, upgrades, and maintenance. Modern fighter jets like the Su-57 are just super expensive to build and maintain, and limited funding means Russia has to carefully balance new acquisitions with sustaining its existing fleet. Another issue lies in aging infrastructure. Honestly, many air bases and support facilities require modernization to keep up with the demands of advanced aircraft and digital warfare systems. Without upgrades, these facilities can become bottlenecks, which reduces readiness and response times. Additionally, Russia faces difficulties in sourcing some high-tech components domestically due to sanctions and export restrictions, which forces reliance on alternative suppliers or indigenous development, and that can delay projects. Maintaining operational readiness while transitioning to newer platforms is also a really delicate balancing act. Retiring older aircraft too quickly risks gaps in capability, while keeping them too long strains resources and logistics. Furthermore, pilot shortages and the need for continuous advanced training add even more complexity to sustaining an effective force. These challenges don't negate Russia's air power, but they do highlight the realities of modern military development. Overcoming these hurdles is going to require strategic planning, investment, and innovation. Russia's ability to address these limitations will ultimately shape how effectively its air force can project power and defend its interests in the years ahead. Role in hybrid and regional conflicts. When air power meets real-world conflict, theory turns into hard-earned experience. Russian air forces have actively participated in hybrid and regional conflicts over the past decade, using these engagements as live testing grounds for tactics, technology, and operational concepts. Syria, for instance, became a proving ground where Russia deployed a mix of advanced fighters, bombers, drones, and electronic warfare systems to support ground operations and test new weapons under combat conditions. These missions provided invaluable data on the effectiveness of precision strikes, air defense suppression, and coordination with other military branches. Similarly, ongoing involvement in Ukraine has pushed Russian air power to adapt rapidly to evolving threats, including countering Western-supplied air defense systems and drones. These conflicts have exposed both strengths and vulnerabilities, which has driven accelerated modernization and tactical innovation. The experience gained has influenced pilot training, drone deployment strategies, and electronic warfare tactics, making the Russian Air Force more battle-hardened and versatile. Moreover, these regional engagements highlight Russia's ability to project air power in complex environments where conventional warfare blends with asymmetric threats. This practical application of air power ensures that Russia's aerial capabilities are not just theoretical, but tested and refined in the crucible of conflict. As a result, Russian air power in 2025 is shaped by real combat experience, making it a dynamic force that continues to evolve in response to modern warfare's challenges and demands. Future outlook and developments. So, what will the future of Russian air power look like beyond 2025? The answer, honestly, lies in a bold vision that combines cutting-edge technology with strategic innovation to maintain and expand air superiority. Hypersonic weapons are at the forefront of this evolution, promising to revolutionize strike capabilities by delivering ultra-fast, hard-to-intercept attacks that can overwhelm enemy defenses. Russia is actively integrating these weapons into its bomber and missile platforms, aiming to create a new level of deterrence and battlefield dominance. Alongside hypersonics, the expansion of drone fleets, especially autonomous and swarm technologies, will totally redefine how Russia conducts reconnaissance and offensive operations, allowing for more flexible, persistent, and cost-effective missions. Stealth technology is also evolving, with continuous improvements to aircraft like the Su-57, and potential new designs that enhance survivability in increasingly contested airspaces. Beyond hardware, Russia is investing heavily in artificial intelligence and network-centric warfare, enabling faster data sharing, improved targeting, and more coordinated multi-domain operations. This future-focused approach really reflects an understanding that tomorrow's air battles will be fought not just with speed and firepower but with information dominance and technological edge. While challenges remain, Russia's commitment to innovation ensures its air force will remain a formidable force capable of adapting to emerging threats and maintaining strategic influence. The trajectory of Russian air power is clear, a blend of advanced weapons, smart technology, and integrated systems designed to secure its place as a dominant aerial power well into the next decade and beyond. Thanks for watching this deep dive into Russian air power with InnoVision Tech. If you enjoyed the video and want to stay updated on the latest in technology and innovation, make sure to hit that subscribe button and ring the bell icon so you never miss an update. We'd love to hear your thoughts. Drop a comment below and tell us what fascinates you most about modern air forces or what topics you want us to cover next. Stay curious, and let's explore the future of tech together. Out that in 2022, a fridge-sized probe named DART smashed into asteroid Dimorphos and knocked it off course by a jaw-dropping 32-minute orbital shift, the first time humanity physically steered a celestial body. That single cosmic punch proved we're no longer spectators in the universe, we're players with a game-changing playbook. Here's the kicker: just one gentle nudge a decade early can send an extinction-level asteroid harmlessly past Earth. Did you know a spacecraft weighing less than a truck can rewrite planetary fate? The DART mission. On a seemingly ordinary autumn day in 2021, humanity quietly launched what would become our species' first real attempt at cosmic self-defense. But nobody could have predicted just how dramatically we'd exceeded our wildest expectations. The Double Asteroid Redirection Test, better known as DART, wasn't just another space mission collecting dust samples or taking pretty pictures. This was different. This was us literally punching an asteroid in the face to see if we could save ourselves from extinction. The target was Dimorphos, a football stadium-sized moon orbiting the larger asteroid Didymos, sitting safely 7 million miles away from Earth, far enough that we couldn't accidentally cause an apocalypse while learning how to prevent one. For nearly a year, This refrigerator-sized spacecraft traveled through the cosmic void with one simple job: crash into an asteroid at 14,000 miles per hour and see what happens. Scientists expected a gentle nudge, maybe shortening Dimorphos's 11-hour 55-minute orbit by about 10 minutes. That would have been revolutionary enough. But when September 26, 2022 arrived and DART completed its kamikaze mission, the results left every space scientist on Earth speechless. The orbit didn't just change by 10 minutes, it changed by 32 minutes. 3 times more than predicted. Suddenly, we weren't just capable of planetary defense, we were apparently really good at it. Impact Results Analysis. 3 weeks after DART's spectacular collision, scientists around the world were hunched over their telescopes, frantically trying to figure out why their carefully calculated predictions had just been obliterated by reality. The Johns Hopkins Applied Physics Laboratory had expected a modest 10-minute change in Dimorphos's orbit, a result that would have made headlines and proven humanity could defend itself against cosmic threats. Instead, their instruments were showing something that seemed almost impossible. A 32-minute orbital shift that left astrophysicists questioning everything they thought they knew about asteroid impacts. Ground-based observatories from Chile to Hawaii confirmed the same jaw-dropping numbers, while NASA's Deep Space Network tracked the aftermath with unprecedented precision. But here's where the story gets absolutely wild. This wasn't a measurement error or some cosmic fluke. The enhanced momentum change was real, and it was caused by something nobody had fully anticipated. When DART slammed into the loose, rocky surface of Dimorphos at 6.14 kilometers per second, it didn't just create a simple crater like hitting solid bedrock would. Instead, it triggered a massive ejection of debris that continued streaming away from the asteroid for weeks, acting like a natural rocket engine pushing Dimorphos even further off course. The European Southern Observatory captured spectacular images of this debris tail stretching across space, resembling a comet's magnificent plume, but created entirely by human engineering rather than solar radiation. Momentum enhancement discovery. What started as a simple physics equation suddenly became the key to unlocking one of space science's biggest mysteries: why DART's impact was so devastatingly effective when it should have been just a gentle tap. The answer lies in something called the momentum enhancement factor, a concept that sounds boring but represents one of the most exciting discoveries in planetary defense history. When DART crashed into Dimorphos, it didn't just transfer its own momentum like a billiard ball hitting another ball. Instead, it created something far more powerful, a continuous rocket-like thrust that kept pushing the asteroid long after the initial collision had ended. Scientists at NASA's Goddard Space Flight Center calculated this enhancement factor to be between 2.2 and 4.9 times stronger than the direct impact alone, meaning the debris cloud was doing most of the heavy lifting and changing the asteroid's path. This wasn't just space dust floating away, it was high-velocity material ejected at hundreds of meters per second, creating thrust in the opposite direction, like a natural engine firing for weeks. The Lowell Observatory tracked this phenomenon as chunks of Dimorphos continued streaming away from the asteroid, each piece adding to the momentum change. What makes this discovery absolutely game-changing is that it proved asteroids aren't just sitting ducks waiting to be pushed around. They're dynamic systems that can amplify our defensive efforts in ways we never imagined possible, turning a modest spacecraft impact into a cosmic home run. Asteroid Structure Insights. When DART obliterated its target, it accidentally solved a decades-old puzzle that had been driving asteroid scientists absolutely crazy. What are these mysterious space rocks actually made of? The impact didn't just change Dimorphos's orbit, it literally tore the asteroid apart and revealed its deepest secrets in real time. What scientists discovered completely revolutionized our understanding of asteroid composition and structure. Dimorphos wasn't the solid, monolithic rock that many had imagined, but rather what researchers call a rubble pile, essentially a loose collection of boulders, pebbles, and dust held together by nothing more than weak gravitational attraction. When DART struck this cosmic sandcastle at 14,000 miles per hour, it triggered a cascading avalanche effect that continued for months afterward. The European Space Agency's telescopic observations showed material continuously streaming away from the asteroid, creating a debris tail extending over 10,000 kilometers into space. Ground-based observatories worldwide, including the Atacama Large Millimeter Array, detected spectroscopic signatures revealing the asteroid's internal composition as chunks of ancient rock that had been floating together for millions of years. This discovery was absolutely crucial because it meant that similar rubble pile asteroids throughout our solar system might be far easier to deflect than anyone had dared hope. The loose structure that made Dimorphos vulnerable to cascading destruction could be humanity's greatest advantage in planetary defense, turning what seemed like our biggest cosmic threats into surprisingly manageable targets for future deflection missions. Strategic implications. When DART succeeded beyond everyone's wildest dreams, it didn't just prove we could defend Earth, it instantly made every existing planetary defense strategy completely obsolete overnight. Military strategists, space agencies, and international defense organizations suddenly found themselves staring at calculators showing numbers that seemed too good to be true, forcing them to tear up decades of carefully planned asteroid deflection scenarios. The Planetary Defense Coordination Office at NASA immediately began emergency revisions to their threat assessment protocols, realizing that their previous models had been based on fundamentally flawed assumptions about asteroid behavior. If rubble pile asteroids like Dimorphos could be deflected with 3 times more efficiency than predicted, then the minimum warning time needed to protect Earth from cosmic impacts had just been dramatically reduced. But here's the twist that kept defense planners awake at night. This incredible effectiveness came with a terrifying flip side. While rubble pile asteroids might be easier to deflect, solid metallic asteroids could prove nearly impossible to budge with current technology. The International Asteroid Warning Network frantically began updating their classification systems, realizing that asteroid composition was now more critical than size when determining threat levels. Countries like China and members of the European Space Agency announced accelerated development of their own planetary defense capabilities, recognizing that the DART mission had just shifted the entire geopolitical landscape of space security. What started as a simple test had accidentally triggered a new space race focused not on exploration, but on survival. Hera mission planning. Before DART's debris had even settled, space agencies across Europe were already scrambling to launch the most ambitious forensic investigation in cosmic history, a mission that would turn the impact site into humanity's first crime scene analysis laboratory in deep space. The European Space Agency had been planning the Hera mission long before DART exceeded all expectations, but the spectacular success suddenly transformed what was meant to be a simple follow-up into the most crucial space mission of the decade. Scheduled for launch in October 2024, Hera carries 2 revolutionary CubeSats named Juventus and Milani that will act like cosmic detectives, examining every detail of the crater DART blasted into Dimorphos's surface. These aren't just ordinary satellites. They're equipped with ground-penetrating radar, advanced spectrometers, and precision imaging systems capable of mapping the asteroid's internal structure down to the meter level. Hera will spend months hovering around the Didymos system, measuring exactly how Dimorphos's mass, shape, and rotation changed after the impact, while its CubeSats deploy to different positions for triangulated analysis. The mission's primary goal is answering the million-dollar question that DART left hanging. Exactly what happened during those crucial milliseconds of impact that caused such an unexpectedly powerful deflection? ESA's scientists need this detailed forensic data to calibrate their computer models for future planetary defense missions, because the next asteroid heading toward Earth won't be a test. It will be the real deal and will need every advantage possible. Planetary defense evolution. So September 2022 marked the exact moment when planetary defense stopped being science fiction and became humanity's newest branch of warfare, not against each other, but against the universe itself. The success of DART, honestly, sent shockwaves through the global space community that extended far beyond NASA's laboratories, fundamentally reshaping how every nation on Earth approaches the existential threat of asteroid impacts. What had been theoretical discussions in academic conferences suddenly became urgent strategic priorities, requiring immediate international cooperation and massive funding allocation. The International Asteroid Warning Network found itself at the center of a completely new type of arms race, where the goal wasn't military dominance but species survival. Countries that had never seriously considered space-based threats began establishing their own planetary defense programs almost overnight. China announced plans for their asteroid deflection demonstration mission by 2030, while the European Space Agency accelerated development of the 3I telescope network, designed to detect potentially hazardous objects decades earlier than current systems. Even smaller nations started contributing to global asteroid monitoring networks, recognizing that cosmic threats don't respect international borders. The United Nations Office for Outer Space Affairs established new protocols for coordinating planetary defense responses because, unlike any previous human challenge, asteroid deflection requires unprecedented global cooperation. Military strategists from around the world began studying DART's results not for weapons development, but for understanding how kinetic impactors could be scaled up for larger threats. The mission had, kind of accidentally, created a template for humanity's first truly unified defense system against an external threat that could end civilization as we know it. Mission success redefinition. Sometimes the most spectacular victories create, well, the most dangerous problems, and DART's overwhelming success forced scientists to completely rewrite the rulebook on what actually counts as mission success in planetary defense. The 32-minute orbital change that had everyone celebrating suddenly became a cautionary tale about the double-edged sword of, exceeding expectations in space. NASA's Planetary Science Division found themselves facing an unprecedented challenge. If a relatively small spacecraft could alter an asteroid's path by more than 26 times the minimum success criteria, what happens when we need surgical precision rather than overwhelming force? The original mission parameters had been designed around achieving at least a 73-second orbital change to prove the concept worked, but the massive 1,920-second shift they actually achieved revealed a, honestly terrifying reality about real-world asteroid deflection scenarios. Mission planners at the Johns Hopkins Applied Physics Laboratory began developing entirely new modeling software to predict these enhanced momentum effects for different asteroid types, because the next deflection mission might need to thread the cosmic needle with millimeter precision. The problem isn't just hitting an asteroid anymore, it's hitting it with exactly the right amount of force to save Earth without accidentally creating secondary threats or debris clouds that could, persist for decades. Future planetary defense missions will require computer simulations so accurate they can predict not just where an asteroid will go, but exactly how fast it'll get there. Because in real emergency scenarios, there's just no room for pleasant surprises that exceed expectations by 2,600%. Debris management and safety concerns. Nobody expected DART's triumphant asteroid collision to create humanity's first cosmic littering problem. But the spectacular debris cloud streaming away from Dimorphos suddenly forced space agencies to confront an entirely new category of planetary defense complications. While the 10,000-kilometer debris tail looked absolutely magnificent through telescopes and proved the mission's effectiveness, it also revealed a sobering reality about large-scale asteroid deflection operations. Every successful impact creates a potentially hazardous cloud of high-velocity fragments that must be tracked and managed for months or even years afterward. The Space Surveillance Network found itself monitoring hundreds of debris particles traveling at several hundred meters per second, each piece following its own unpredictable trajectory through space. For future missions involving Earth-crossing asteroids, this debris management challenge becomes exponentially more complex and dangerous. Mission planners at NASA's Jet Propulsion Laboratory realized that deflecting a kilometer-wide asteroid heading toward Earth could create millions of fragments, some potentially large enough to cause regional devastation even if the primary threat is eliminated. The European Space Agency's debris tracking models showed that impact-generated fragments could persist in unstable orbits for decades, creating long-term navigation hazards for spacecraft and satellites. This discovery forced planetary defense strategists to develop entirely new protocols for debris field prediction and fragment trajectory analysis, because saving Earth from one cosmic threat while accidentally creating dozens of smaller ones would be a Pyrrhic victory of cosmic proportions. The irony wasn't lost on anyone. Humanity's greatest defensive success had also created our first lesson in responsible cosmic debris management. Precision requirements for real threats. The clock is ticking faster than anyone realized, and DART's incredible success just taught us the most sobering lesson in cosmic defense. Early warning isn't just important, it's literally the difference between survival and extinction for our entire species. When scientists calculated what DART's 32-minute orbital change would mean for a real Earth-crossing asteroid, the numbers were both thrilling and, honestly, terrifying. That same deflection force applied to a genuine threat detected 10 years in advance could alter its trajectory by thousands of kilometers, easily sending it safely past our planet. But here's the nightmare scenario that keeps planetary defense experts awake at night. If that same asteroid were detected just 6 months before impact, even DART's spectacular performance wouldn't be enough to save us. The Center for Near-Earth Object Studies at JPL now emphasizes that the precision requirements for real threats make early detection more critical than ever before. A deflection mission launched decades in advance needs only a gentle nudge, while last-minute interventions require devastating force that could fragment the asteroid into multiple city-killing projectiles. The Catalina Sky Survey and linear detection programs are being dramatically expanded because DART proved we have the technology to defend Earth, but only if we spot the threat with enough time to act. The mission's legacy isn't just that humanity can change an asteroid's path, it's that we must find every potential killer asteroid years before it finds us, because in planetary defense, timing isn't everything, it's the only thing that matters. And that's the incredible story of how DART didn't just hit an asteroid, it revolutionized humanity's cosmic defense strategy and proved we're ready to protect our planet from extinction-level threats. The universe just got a little less scary, and space just got a lot more exciting. If you enjoyed diving into this mind-blowing mission, smash that subscribe button and hit the bell icon so you never miss our latest space discoveries and tech breakthroughs here at InnoVision Tech. Drop a comment below. What do you think about humanity's first successful planetary defense test? Until next time, keep looking up. What if I told you that in 2017 humanity received its first confirmed visitor from another star system, and we almost missed it completely? This mysterious object, traveling at 26 kilometers per second, defied every law of physics we thought we understood, accelerating away from the sun without any visible explanation. Here's the mind-blowing part. Some of the world's top scientists now believe we may have just witnessed our first encounter with alien technology. Did you know that Oumuamua is still the only confirmed interstellar object we've ever detected, and it's already gone forever? Oumuamua initial detection. On October 19, 2017, the universe delivered humanity its first confirmed interstellar messenger, and it caught us completely off guard. The Pan-STARRS telescope in Hawaii was conducting routine asteroid surveys when astronomers Robert Warwick and his team spotted something extraordinary streaking across the star field at unprecedented velocity. This wasn't just another space rock cataloged in their database, it was moving too fast, coming from the wrong direction, and following a trajectory that immediately screamed outsider to anyone familiar with solar system dynamics. They named it Oumuamua, a Hawaiian word meaning scout or messenger from afar arriving first, recognizing that this discovery would fundamentally change our understanding of what lurks in the spaces between stars. Within hours of the initial detection, telescopes around the world were frantically tracking this mysterious visitor as it hurtled past Earth at 26 kilometers per second, speeds that dwarfed anything gravitationally bound to our sun. The object had already completed its closest approach to our star and was racing toward the outer solar system, giving scientists only a precious few weeks to study it before it vanished forever into the cosmic void. What made this discovery truly groundbreaking wasn't just that Oumuamua came from another star system, it was the first interstellar object ever detected passing through our cosmic neighborhood, opening an entirely new field of astronomy and raising profound questions about what else might be drifting silently through the galaxy, undetected by our current observation methods. Classification challenges. The moment scientists began analyzing Oumuamua's properties in detail, they realized they were dealing with something that defied every classification system developed over centuries of astronomical observation. Initially tagged as Asteroid A/2017 U1 based on preliminary observations, the object quickly demonstrated characteristics that challenged this hasty designation. Unlike typical asteroids which maintain relatively stable brightness patterns as they rotate, Oumuamua's luminosity varied dramatically by a factor of 10 as it tumbled chaotically through space, suggesting an extremely unusual elongated shape that was unprecedented in solar system astronomy. Even more puzzling, despite approaching within 0.25 astronomical units of the Sun, close enough to vaporize surface materials on most comets, it displayed absolutely no coma, tail, or any other signs of outgassing that should accompany such solar heating. NASA's Jet Propulsion Laboratory and international astronomy teams spent months in heated debates, frantically analyzing spectroscopic data and photometric measurements while flip-flopping between asteroid and comet classifications as new observations contradicted previous assumptions. The confusion reached such levels that by 2018, the International Astronomical Union was forced to create an entirely new category, officially designating it 1I/Oumuamua, the 1I indicating the first confirmed interstellar object, and establishing a new nomenclature system for future discoveries. This classification nightmare highlighted how woefully unprepared our taxonomic systems were for objects originating beyond our solar system, forcing the scientific community to acknowledge that Oumuamua might represent a completely unknown class of celestial bodies formed under conditions and processes entirely different from anything occurring within our sun's gravitational influence. Trajectory analysis. When astronomers reverse-engineered Oumuamua's cosmic journey using sophisticated orbital mechanics calculations, they uncovered an epic tale spanning potentially millions of years across the vast emptiness of interstellar space. The comprehensive trajectory analysis performed by international teams at ESA's European Space Operations Center and NASA's Jet Propulsion Laboratory revealed that this interstellar wanderer had been drifting through the galaxy long before our solar system had even settled into its current configuration of planets and orbital resonances. Using precise astrometric measurements from multiple observatories, researchers initially calculated that tracing its path backward pointed toward the direction of Vega in the constellation Lyra, one of the brightest stars in our night sky. However, deeper analysis incorporating proper motion corrections and galactic rotation models revealed a far more complex story that challenged simple origin theories. The object would have needed approximately 600,000 years to travel from Vega's current position to reach our solar system, yet stellar motion calculations proved that Vega wasn't located in that position 600 millennia ago due to the constant movement of stars through galactic space. This startling discovery proved that Oumuamua was a true galactic nomad with no clear stellar home, having wandered through multiple stellar neighborhoods during its cosmic odyssey. Its hyperbolic trajectory, a mathematically defined path that curves around the Sun once before heading back to interstellar space forever, indicated approach speeds of 44 kilometers per second relative to our Sun at perihelion. Unlike the elliptical orbits of comets and asteroids gravitationally bound to our star, Oumuamua possessed more than enough kinetic energy to escape permanently into the cosmic wilderness, never to return to our solar system again. Photometry and shape analysis. The light measurements of Oumuamua revealed, honestly, the most bizarre shape ever recorded for any natural object in our solar system. Photometric observations conducted by observatories all over the globe, including the Very Large Telescope in Chile and Gemini Observatory in Hawaii, showed brightness variations that, well, could only be explained by an extremely elongated form. Scientists calculated that Oumuamua was at least 10 times longer than it was wide, with dimensions roughly 400 meters by 40 meters, kind of resembling a cosmic cigar tumbling end over end through space. Dr. Karen Meach from the University of Hawaii led international teams analyzing these light curves, discovering the object completed one full rotation every 7.3 hours. The extreme aspect ratio was totally unprecedented. No known asteroid or comet even came close to such proportions. Some researchers, including Dr. Shmuel Bieli, proposed it might be even flatter, resembling a cosmic pancake rather than a cigar, which honestly would make it even more unusual. The surface appeared reddish, similar to objects in the outer solar system that have been darkened by cosmic radiation over billions of years. However, Oumuamua reflected only about 4% of incident sunlight, making it darker than charcoal. This combination of extreme elongation, dark surface, and rapid tumbling motion created a unique signature that really challenged existing models of how small bodies form and evolve in space, suggesting formation processes completely unlike anything occurring in our solar system. Acceleration anomaly. The discovery that, honestly, shattered every conventional explanation came when precise tracking revealed Oumuamua was accelerating away from the Sun in ways that just defied physics. Dr. Marco Michelli and his international team published their groundbreaking findings in Nature journal in June 2018, documenting a small but measurable non-gravitational acceleration of approximately 4.92 times 10 to the minus 6 meters per second squared. This wasn't measurement error. Multiple independent observations confirmed that Oumuamua was actually speeding up as it moved away from our star. For typical comets, acceleration like this makes perfect sense. Frozen gases sublimate near the sun, creating jets that act like tiny rocket engines. However, Oumuamua showed absolutely no signs of this outgassing activity. No visible coma, no tail, no gas emissions detectable by any instrument. The Hubble Space Telescope conducted follow-up observations that confirmed the anomalous motion while ruling out systematic errors or unknown forces. This acceleration was too large to be explained by solar radiation pressure alone, yet too small to be caused by gravitational influences from planets or other bodies. The mystery deepened when scientists realized that whatever was causing this acceleration appeared to be acting continuously and smoothly, rather than in bursts typical of comet outgassing. This unprecedented behavior forced astronomers to consider possibilities they had never seriously contemplated. Either Oumuamua represented a completely unknown type of natural phenomenon or, well, something artificial was responsible for its strange motion through our solar system. Spitzer observations. NASA's Spitzer Space Telescope conducted humanity's final attempt to solve the Oumuamua mystery before the object disappeared forever beyond the reach of Earth's instruments. During November 2017, this infrared observatory pushed its capabilities to the absolute limit, conducting some of the most sensitive thermal measurements ever attempted on such a distant small object. Dr. Davide Farnocchia and his team at JPL analyzed the resulting data, hoping to detect the warm signatures of outgassing that might explain the acceleration anomaly. Instead, Spitzer's observations only deepened the puzzle. The telescope detected virtually no thermal emission from Oumuamua, setting strict upper limits on any dust or gas production. If the object were behaving like a normal comet, even minimal outgassing should have created detectable infrared signatures, as solar heating warmed expelled material. The absence of such emissions meant that if outgassing was responsible for the acceleration, it had to be composed of materials completely invisible to infrared detection. Spitzer's measurements also refined estimates of Oumuamua's size and reflectivity, suggesting it was smaller than initially calculated, possibly only 100 to 200 meters in its longest dimension. This smaller size would actually amplify any outgassing effects, making the lack of detectable emissions even more mysterious. The final Spitzer observations in January 2018 showed Oumuamua continuing its anomalous acceleration while remaining thermally invisible, leading scientists to conclude that conventional comet behavior could not explain this object's properties and motion through our solar system. Artificial origin hypothesis. When every natural explanation failed, Harvard University's Professor Avi Loeb and postdoctoral researcher Shmuel Bialy proposed the unthinkable in a paper published in the Astrophysical Journal Letters in October 2018. They suggested that Oumuamua might actually be artificial, specifically a light sail created by an extraterrestrial civilization. This hypothesis, honestly, elegantly explained the acceleration anomaly. A thin, flat object could be pushed by solar radiation pressure without requiring any outgassing. For this mechanism to work, Oumuamua would need to be incredibly thin, less than 1 millimeter thick, while still maintaining its observed dimensions. Loeb proposed it could be debris from alien technology, possibly millions of years old, just drifting through space like cosmic junk from a long-dead civilization. The light sail hypothesis explained not only the non-gravitational acceleration, but also the object's extreme elongation and its unusual tumbling motion. Dr. Loeb argued that extraordinary claims require extraordinary evidence, but, extraordinary evidence also requires extraordinary hypotheses. The scientific establishment reacted with fierce criticism, with many astronomers arguing that invoking alien technology violated Occam's razor, the principle favoring simpler explanations. However, supporters pointed out that dismissing the possibility without proper investigation could actually represent a form of cosmic prejudice. The debate raged across scientific journals and conferences, with researchers split between those demanding more conventional explanations and others willing to consider that humanity had encountered its first piece of alien technology, even if we couldn't definitively prove it. dark comet theory. Dr. Daryl Seligman from the University of Chicago proposed a revolutionary alternative that really challenged our understanding of comet composition and interstellar chemistry. The dark comet hypothesis, which was published in the Astrophysical Journal back in 2020, suggested that Oumuamua could actually be made mostly of frozen molecular hydrogen. In the extreme cold of interstellar space, where temperatures are around 14 Kelvin, hydrogen can freeze into solid ice that would stay stable for millions of years. As Oumuamua got closer to our sun, this hydrogen ice would sublimate directly into gas, but unlike water vapor or other typical comet materials, hydrogen gas is almost completely invisible to most astronomical instruments. This invisible outgassing could explain the mysterious acceleration without creating any visible coma or tail. The theory goes on to suggest that Oumuamua formed billions of years ago in a giant molecular cloud. Those vast regions of space where gas and dust come together before forming new stars and planetary systems. These environments could create really unique conditions for hydrogen ice to build up, making objects unlike anything we've seen in our own solar system. Seligman's calculations showed that a hydrogen iceberg about the size of Oumuamua could stay intact during its journey through interstellar space, and provide enough outgassing to explain the observed acceleration. This hypothesis opened up the possibility of an entirely new class of interstellar objects that might be drifting undetected all over the galaxy, basically invisible to our current observation methods, because their outgassing doesn't produce any visible signatures that our telescopes can pick up. Dark comet classification. The implications of the dark comet theory went way beyond just Oumuamua. It could totally revolutionize the way astronomers classify small bodies in space. Researchers at NASA's Jet Propulsion Laboratory started developing new classification systems to account for objects that show non-gravitational acceleration, but without any visible activity. Scientists began to propose distinguishing between small dark comets like Oumuamua, which came from interstellar space, and potentially large dark comets that might actually exist within our own solar system, just unrecognized up until now. Dr. Daryl Seligman and his colleagues even identified several objects in the solar system database that showed unexplained acceleration without obvious outgassing, suggesting that dark comets might be way more common than we ever imagined. The new classification parameters included things like thermal emission signatures, spectroscopic properties, and acceleration magnitudes that are really different from what we see with traditional comets and asteroids. This new framework suggested that maybe our telescopes have been missing a whole population of hydrogen-rich objects simply because our detection methods are tuned for water-ice comets and rocky asteroids. The European Space Agency even started to include dark comet detection protocols in their future mission planning, realizing that interstellar visitors could be a lot more common than just the single confirmed case of Oumuamua. Some researchers estimated that if the dark comet hypothesis is correct, the galaxy could have billions of these invisible objects, creating a hidden population of interstellar wanderers that occasionally pass through planetary systems without us even noticing. This whole idea really changes our understanding of how material is distributed across the galaxy, and it suggests that the space between stars could be way more crowded with small bodies than our astronomical models had predicted. Scientific debate. The Oumuamua controversy has basically split the astronomical community into competing camps, each one defending some pretty radically different interpretations of the same data. Team Natural, led by researchers at NASA's Goddard Space Flight Center and the European Southern Observatory, insists that conventional physics has to explain the acceleration anomaly, and they propose things like outgassing of common volatiles or internal changes during solar heating. Then there's Team Artificial, led by Harvard's Avi Loeb and backed by researchers from Tel Aviv University, who argue that the light sail hypothesis deserves serious scientific consideration, and shouldn't just be dismissed because people are skeptical about extraterrestrial explanations. Team Dark Comet, centered around researchers at the University of Chicago and Yale University, is pushing the hydrogen iceberg theory and working on ways to detect similar objects. The debate has been going strong in top scientific journals like Nature, Science, and the Astrophysical Journal since 2018, and honestly, each new analysis seems to make the mystery even deeper. Dr. Alan Fitzsimmons from Queen's University Belfast leads the skeptics, saying that these exotic explanations go against scientific principles. while Dr. Abraham Loeb's supporters counter that extraordinary evidence demands extraordinary hypotheses. Recent studies have even found more solar system objects with similar properties, which could support the dark comet classification. The scientific process is working exactly as it should. Competing hypotheses are driving new observations and new theories. Whether Oumuamua was natural, artificial, or something totally unprecedented, it's already changed astronomy by showing that interstellar objects can really challenge our most basic assumptions about the universe, forcing scientists to broaden their frameworks for understanding cosmic phenomena. So, there you have it. Oumuamua is still one of the greatest mysteries in modern astronomy, challenging just about everything we thought we knew about interstellar objects. Whether it was a natural dark comet, alien technology, or something completely unprecedented, this cosmic visitor has forever changed the way we see our place in the universe. What's your theory? Was Oumuamua our first glimpse of extraterrestrial engineering, or does nature still have more surprises up its sleeve? Drop your thoughts in the comments below. I read every single one. And if you're fascinated by these mind-bending space mysteries, go ahead and smash that subscribe button and hit the bell icon so you never miss the latest discoveries from InnoVision Tech. Until next time, keep looking up. Imagine looking up at the night sky and realizing that something from another star system is silently racing past us at incredible speed. In the summer of 2025, astronomers detected exactly that. A mysterious visitor from the depths of interstellar space that has been traveling for millions of years before finally reaching our solar system. This cosmic wanderer, known as 3I-ATLAS, represents only the third confirmed interstellar object ever discovered. Today we'll explore everything scientists have learned about this extraordinary celestial traveler, and what it reveals about our galaxy. Discovery of 3I-ATLAS. Here's the moment that changed our understanding of interstellar visitors forever. On July 1, 2025, the ATLAS telescope system at Rio Hurtado Observatory in Chile captured images of an unusual moving object racing through space at 61 kilometers per second. The discovery team, led by Larry Deneau from the University of Hawaii's Institute for Astronomy, immediately recognized that this wasn't an ordinary asteroid or comet from our solar system. The object's hyperbolic trajectory and extreme velocity indicated it was following an escape path from our sun's gravitational influence. Initially catalogued as A11PL3Z, the mysterious visitor was positioned 4.5 astronomical units from the sun, approaching from the direction of Sagittarius. What made this detection particularly remarkable was that pre-discovery images dating back to June 14, 2025, revealed the object had been approaching undetected for weeks. The reason for this delayed discovery was its trajectory through the dense star fields near our galaxy's center, where countless background stars made it nearly impossible to spot against the crowded stellar backdrop. Within hours of confirmation, observatories worldwide began tracking this rare interstellar wanderer, setting the stage for one of astronomy's most significant discoveries. ATLAS Survey System. But here's where this discovery became truly historic and earned its place in astronomical records. After extensive trajectory analysis by the Minor Planet Center, the object received its official designation as 3I-ATLAS, where 3I signifies it as the third confirmed interstellar object in human history. This places it alongside the famous 1I Oumuamua discovered in 2017, and 2I Borisov found in 2019. However, 3I-ATLAS quickly distinguished itself from its predecessors in a remarkable way. Karen Meach from the University of Hawaii and her international team confirmed on July 2, 2025, that the object was displaying clear cometary activity. Unlike Oumuamua, which remained enigmatically inactive throughout its visit, 3I-ATLAS developed a visible coma and tail almost immediately after discovery. Observations from the Nordic Optical Telescope revealed the comet was clearly active with a distinctive tail measuring at least 25,000 kilometers in length. John Tonry, principal investigator of the ATLAS project, noted that this discovery validated their sky survey system's capability to detect rare astronomical phenomena. The rapid identification of cometary activity made 3I-ATLAS the second confirmed interstellar comet, providing scientists with an unprecedented opportunity to study active sublimation processes in a visitor from another star system. Object classification and naming. Now prepare to be amazed by the sheer scale of this interstellar giant. Recent observations conducted by Marco Micheli from the European Space Agency using the Vera C. Rubin Observatory have determined that 3I-ATLAS measures approximately 11.2 kilometers in diameter, making it significantly larger than both previous interstellar visitors combined. This massive size has profound implications for scientific study, as larger objects retain more of their original composition and provide clearer observational targets for detailed analysis. The comet's substantial nucleus is surrounded by an active coma that exhibits a distinctly reddish coloration, remarkably similar to what was observed in 2I Borisov. Darrell Seligman from Michigan State University, who led the initial characterization studies, noted that this color similarity suggests interstellar comets may share common compositional characteristics regardless of their stellar origin. The impressive scale of 3I-ATLAS means it will remain visible to Earth-based telescopes for an extended period, giving researchers months rather than weeks to conduct comprehensive observations. This extended visibility window represents a golden opportunity for the astronomical community to gather unprecedented data about interstellar comet composition, structure, and behavior as it interacts with our sun's radiation and solar wind during its passage through our solar system. Orbital characteristics. Okay, here's something that will really blow your mind about this cosmic time capsule's incredible journey through space. Based on detailed orbital mechanics calculations performed by Davide Farnochia at NASA's Jet Propulsion Laboratory, scientists believe that 3I/ATLAS actually originated from the Milky Way's thick disk region, where ancient stellar populations reside. This means the comet is potentially around 7 billion years old, which is, well, older than our entire solar system by approximately 2.5 billion years. Its epic journey likely began when gravitational perturbations from massive planets or maybe even close stellar encounters ejected it from its birth star system eons ago. For millions of years, this ancient wanderer drifted through the frigid vacuum of interstellar space at temperatures approaching absolute zero, which honestly perfectly preserved its primordial composition like a cosmic freezer. Sam Dean, an amateur astronomer who helped identify additional pre-discovery observations, contributed to tracking the comet's path backwards through time. The comet's trajectory suggests it has been traveling through the galaxy's spiral arms, potentially witnessing the formation and destruction of countless star systems during its incredible voyage. This preservation makes 3I/ATLAS an invaluable scientific specimen, carrying within its frozen nucleus the chemical signatures and formation conditions that existed in a distant star system billions of years ago, offering unprecedented insights into galactic evolution and early planetary system formation processes. Physical properties. But here's what makes this discovery even more extraordinary: the unprecedented international scientific collaboration that made it possible. The research effort was spearheaded by Michigan State University's Darrell Seligman, who coordinated with a global network of observatories and research institutions to maximize observation time and data quality. Robert Warwick from the University of Western Ontario, who previously discovered 1I Oumuamua, provided crucial expertise in interstellar object identification and tracking protocols. The collaborative team included researchers from the European Southern Observatory, NASA's Goddard Space Flight Center, and the Harvard-Smithsonian Center for Astrophysics, really demonstrating how modern astronomy relies on rapid international cooperation. Grigory Fedoretz from Queen's University Belfast contributed orbital dynamics expertise, while Tony Farnham from the University of Maryland provided cometary activity analysis. This coordinated effort represents one of the most comprehensive rapid response campaigns in astronomical history, with over 50 professional observatories and numerous amateur astronomers contributing observations within the first month of discovery. The team's ability to quickly organize this global response ensured that critical early observations were captured before the comet's activity levels changed, maximizing the scientific return from this rare interstellar visitor and establishing new protocols for future interstellar object studies. Comet activity features. Now let's trace the incredible path this ancient wanderer will take through our solar system over the coming months. 3I/ATLAS will reach its closest approach to the Sun, called perihelion, on October 29, 2025, at precisely 11:41 Universal Time. At this crucial moment, It will be positioned 1.36 astronomical units from the Sun, that's about 203 million kilometers away, perfectly situated between the orbits of Earth and Mars. This optimal distance means the comet will experience significant heating without being destroyed by extreme solar radiation. During its approach phase, the comet will have several notable planetary encounters that provide unique observational opportunities. On October 3, 2025, it will pass just 0.19 astronomical units from Mars, only 28 million kilometers away, potentially allowing Mars-based instruments to conduct close-range observations. Following perihelion, the comet will swing past Venus on November 3, 2025 at a distance of 0.65 astronomical units. Most importantly for Earth-based observers, our planet remains completely safe throughout this cosmic dance. The closest 3I-ATLAS will approach Earth is 1.8 astronomical units on December 19, 2025. That's about 270 million kilometers away, providing excellent viewing conditions while maintaining a comfortable safety margin. This trajectory offers astronomers multiple observation windows from different vantage points throughout the solar system. Amateur contributions. Here's where the scientific excitement reaches its peak: the detailed analysis of this interstellar visitor's composition and structure. Spectroscopic observations conducted by Alan Fitzsimmons from Queen's University Belfast using the Gemini Observatory have revealed that 3I-ATLAS is composed primarily of water ice, silicate minerals and organic compounds similar to comets in our own solar system. However, the presence of exotic isotopic ratios in its gas emissions suggests formation conditions significantly different from our local environment. Bin Yang from the European Southern Observatory detected unusual concentrations of deuterium-rich water vapor, indicating the comet formed in an extremely cold environment around a different type of star. As the comet approaches the Sun, increasing solar radiation is causing accelerated sublimation of volatile ices, revealing deeper layers that have remained frozen for billions of years. Jacqueline Keane from Boston University has identified traces of carbon monoxide and methane in the comet's tail, providing insights into the chemical conditions of its birth star system. The James Webb Space Telescope, under observations led by Stephanie Malam from NASA Goddard, has been scheduled to conduct detailed infrared spectroscopy to identify complex organic molecules that might exist within the comet's nucleus. These compositional studies are providing unprecedented insights into star formation processes and the distribution of life-building molecules throughout our galaxy. Surface composition. But here's what makes this observation campaign truly revolutionary: the unprecedented coordination of space-based and ground-based telescopes working together. Paul Chodas from NASA's Center for Near-Earth Object Studies has coordinated orbital predictions that allow telescopes to track the comet with extreme precision. The Hubble Space Telescope, under the direction of Matthew Knight from the Naval Research Laboratory, captured high-resolution images on July 21, 2025 that revealed intricate details of the comet's coma structure and dust distribution patterns. Ground-based facilities including the Very Large Telescope in Chile and the Keck Observatory in Hawaii have been providing continuous monitoring of the comet's brightness changes and spectral evolution. Quanzi Ye, from the University of Maryland, has been leading photometric studies that track how the comet's activity levels change as it approaches the Sun. The NEOWISE Space Telescope has been measuring infrared emissions to determine the comet's temperature distribution and internal heat sources. This coordinated campaign represents the most comprehensive study of an interstellar object ever conducted, with data collection continuing through September 2025, before the comet passes too close to the Sun for safe observation. The wealth of data being collected will provide material for scientific studies for decades to come, advancing our understanding of interstellar chemistry and planetary system formation processes. Interstellar object density. Now here's something that sounds like science fiction but is being seriously considered by space agencies worldwide. Atsuhiro Yaginuma, an undergraduate researcher working with Daryl Seligman at Michigan State University, is conducting detailed trajectory analysis to determine whether a rapid spacecraft mission to 3I-ATLAS might be feasible. The challenge is enormous. Intercepting an object moving at 61 kilometers per second would require unprecedented propulsion technology and launch timing precision. Julie Castillo-Roges from NASA's Jet Propulsion Laboratory has has been evaluating existing spacecraft designs that could potentially reach the comet during its closest approach to Earth in December 2025. Such a mission would need to launch within months of the discovery, requiring massive international cooperation and emergency mobilization of space resources. Alan Stern, principal investigator of the New Horizons mission, noted that while technically challenging, the scientific payoff from getting close to an interstellar object would be revolutionary. A successful intercept could provide direct samples of materials from another star system, potentially containing organic compounds or even microscopic signs of extraterrestrial life. Even if a full intercept proves impossible, the research being conducted is advancing rapid response space mission capabilities and establishing protocols for future interstellar object encounters. The mere possibility represents a remarkable leap in humanity's ability to explore beyond our solar system. Origins and age speculation. Finally, here's the most profound implication of this discovery for the future of astronomy and our understanding of the cosmos. The detection of 3I-ATLAS, following Oumuamua and Borisov, is providing statistical evidence that interstellar objects are far more common than previously estimated. Mark Norris, from the University of Central Lancashire, has calculated that approximately one interstellar object larger than 100 meters passes through our solar system every year, though most remain undetected. Robert Jedicke from the University of Hawaii estimates that the ATLAS survey system, with telescopes in Hawaii, Chile, and South Africa, will detect several interstellar objects annually as technology improves. The Vera Rubin Observatory, scheduled to begin full operations in 2025, is expected to revolutionize interstellar object discovery with its ability to scan the entire visible sky every few nights. Michelle Bannister from the University of Canterbury predicts that within a decade, we'll have discovered dozens of these cosmic wanderers, providing a statistical sample large enough to understand galactic dynamics and planetary system evolution. Each new discovery adds pieces to the puzzle of how materials and potentially life itself might be distributed throughout our galaxy. 3I-ATLAS isn't just a single remarkable discovery, it's opening an entirely new field of astronomy that studies the messengers traveling between star systems, carrying secrets from across the galaxy. From its ancient origins in the thick disk of our galaxy to its spectacular journey past our sun, 3I-ATLAS has revolutionized our understanding of interstellar visitors and the materials that travel between star systems. This cosmic time capsule, preserved for billions of years in the cold of space, continues to reveal secrets about distant worlds and the formation of our galaxy itself. As we track its departure back to interstellar space, we can only wonder what other mysteries await discovery. Like, share, and subscribe to InnoVision Tech for more cosmic revelations.